Good morning, everyone. Welcome to the first of this week's webinars hosted by Rockflow Dynamics. My name is Joanne from RFD Aberdeen team, and today I'm hosting this session with my colleagues Tom Marsh and Elliot Moore, both also from our Aberdeen team. Thanks to everyone who's joined us for our recent webinars and joined us today as well. Hope you're all staying safe and well. RFD teams are continuing to work from home and support our clients remotely, so if you need any assistance, just get in touch with us. Best place to keep up to date with our activity is our LinkedIn page, so make sure you're following to hear all about upcoming webinars and other tNavigator updates. So welcome. If you haven't joined one of our webinars before, this is how it will work. All attendees online today will have their microphone automatically muted. So if you would like to ask a question, please use the control panel on the side of your screen and we'll answer as many of those as we have time to at the end. If we don't answer your question live, we will follow up with you after. The session is being recorded and that will be uploaded to our YouTube channel later on, so you can also watch there or share with others. If you'd like any more information, you can always drop us an email, asktnav@rfdyn.com. In today's session, Tom is going to give you a quick overview of our static modelling tools, followed by a demonstration of a Facies modelling workflow from Elliot. We've got a variety of webinar topics over the last few weeks, and all the previous sessions are available on the YouTube channel. We're going to have a break next week, and then we'll be back on the 16th with some more webinars for you, so we'll share more details about that very soon. If there's any topics that you would like to see in future webinars, you can easily let us know and we'll try to include those for you. In our webinars, we are showing you a wide range of demonstrations from each stage of the integrated workflow inside tNavigator. So if there's a functionality that you maybe haven't heard about before or you'd like to hear more information, don't hesitate to get in touch with one of the team for some more details and trial licenses. So now I will hand you over to Tom to begin the presentation. Thank you, Tom.
Thank you, Joanne, and thanks for everyone who has joined us on today's talk. Just to introduce myself, my name is Tom Marsh. I am the Geoscience Business Development Manager here in UK, based in Aberdeen. So a little background about myself. After graduating my Masters in Petroleum Geoscience nearly a decade ago now, I joined Summergen to support their G&G products for roughly 6 years. And then advanced to Rockflow Dynamics, becoming Geoscience Business Development Manager, where my main requirements now involve guiding and pushing technical development plans, showcasing new software updates, and mainly pretty much around geoscience workflows. But more recently, actually, which is a little bit more exciting for me, actually, is being involved and supporting integrated static and dynamic studies, basically enhancing operators and our clients with more informed decisions when it comes down to uncertainty analysis and assisted history match analysis, especially now that we can link both the static and dynamic together in the same interface through automated workflows. So on the line today with me is Elliot Moore, who is our support geoscientist. Elliot will be the main man today, actually, ultimately taking you through the webinar, which is on specifically Facies modelling. He's been with us for pretty much a year now after graduating from the University of Aberdeen with a Masters in Geology. Elliot is currently supporting our geoscience community a lot, I would say, answering a lot of our clients' queries and supporting any technical questions that are directed to us on geoscience, on G&G workflows. Okay. So I just wanted to really just talk about the product specifically on my side, and then I'll hand you over to Elliot, just for those who perhaps are not so familiar with tNavigator. So those that use tNavigator and are aware of its current capabilities and functionality will be familiar with its performance, the speed, and actually the computational power to run simulations, right? And in fact, it's probably safe to say that our simulation has taken off and transformed the ability, in some cases, to even simulate complex fields or allow companies to run enough analysis in a timely manner to make faster and more informed decisions. However, that said, we are much more than that. And this is where sort of we come in, LAI, geoscience community, because now we have the functionality to embed your static modeling best practices. The functionality has been completely integrated in the same platform, allowing you to combine actually your static and dynamic modeling workflows in a single interface, working with multiple CPUs and GPUs, all within a parallel computational engine. But actually, like that's all great. But what does it actually mean for the geoscience workflows? So here on the screen, you see some, I guess, like some buzzwords, right? Performance, scalability, features, fully integration. So what I would like to talk about mainly is the fact that we can run all of our interpolation algorithms, specifically within the geoscience workflows, on the GPU and multiple CPU capabilities. And this includes things like Facies modeling, petrophysical modeling, and any of the interpolation algorithms that are embedded in there. So this actually means when we start to automate our analysis, perhaps under uncertainty workflows, we can benefit from the efficiency and speed and gather much more timely results. Scalability. This also means we can start to think about building our geological grids, right? So if we have the engine, we can build our geological grids at the scale we desire without the need for necessary upscaling when transferring to project or engineers. And consequently, we can then capture and think about the geological detail and the heterogeneity we want to capture in our study, which of course can have an effect on the forward simulation going forward, specifically when it comes around to history matching our wells. And then this really, for this particular slide, moves me on to this topic of full integration, which is pretty much a big buzzword these days in the industry. But with the implementation of our static modeling, we have a truly integrated platform, all written under the same code, line of code, that allows the geologist to complete their static modeling workflow automatically, recording all of their steps as they proceed through the processes, and then having the ability to transfer directly to the engineer, who can then seamlessly continue their workflow in the dynamic domain. And this is all really done in the same graphical user interface and the same environment. So what I want to do really here, this next slide, is really just a quick intro, right? So those that know and have used tNavigator, this is the very first page you will visit before proceeding with any of your projects. So as you see, it really does come apparent that we have much more than the simulation software now. So you'll see the simulation here. But now what we can do is actually host multiple workflows, and it's not just from subsurface; it's actually from surface to surface as well. So the application we're going to talk about today is this geology design, of course. For me, this is where it all begins with the geology. But what I want to talk about is actually what it actually does, which is a question I actually get asked a lot. What capabilities and what functionality do we actually cover within this particular section of tNavigator? So within the sort of last 2 years, being with Flow Dynamics, I've seen so much focus on development, and this is a very, very busy slide. I actually use this slide a lot when I'm presenting, because it's really cool to see the amount of development, and it's just a handful of products, features, algorithms that I've put on there, some of my favorite ones that have been implemented inside, particularly the geology application inside tNavigator over the past couple of years now. So we started off around 7 or 8 years ago with the ability for our engineers to manipulate and make changes to their static model in order to fine-tune the static side before they go into the simulations, right? However, over time, we realized there were huge amounts of support and drive to enhance more complexity into their workflows, and not only from our team and internally, it actually becomes more so from our clients. So we actually listened, and we delivered, and you'll see on the screen here just in the past 15 12 to 15 months, I would say. So there's a handful of development functionality we have thrown onto the platform. And again, ranging from user interface, embedded algorithms, features, to actually re-ensure a sound, fit-for-purpose static model. So over the past couple of years, we have focused on developments, not just on, we do have specific areas of development we focus on, such as wells, seismic, geological interpretation, structural modeling, and reservoir modeling. So now you can see with a platform that now we host the capability of running a full static modeling workflow. Okay, so I'm not going to talk in detail about some of these, but certainly on another webinar, or if you want to know more in detail about a certain workflow within here, just contact us and we'll be delighted to talk about it. But what we can talk generally about is we can now start to talk about how we can build a static model project from scratch, whether that's importing all the static modeling data through various plugins or from raw files. And we can talk about running geological interpretations, whether that's through well correlation, data analysis, or creating geological maps through various means. And then using the interpretation to generate structural framework, and then ultimately building reservoir models through property modeling and things like that. So there's a lot here. I'm just going to finalize my section before I hand over to Elliot. But yeah, there's a lot here now. But however, today we do focus on a specific topic, and this is reservoir modeling. But more specifically, actually Facies modeling. And I get a lot of questions about the type of algorithms that we have within tNavigator, and when it comes down to specifically Facies modeling, actually. So hopefully today, Elliot will go through this with you. For this webinar, you will see a variety of methods used to interpret your Facies and used to generate your Facies model. We have a conceptual image here on the left, which you see. And actually, what we want to do here is actually bring this sort of schematic conceptual image into our geological model, as well as our well data. We will focus on this typical sort of plastic environment, as you see, which would be composed geologically of a variety of geometries as we sort of feed into the system. So hopefully we'll use various algorithms that you will see today, which Elliot will demonstrate, to try and capture different objects, geometries, and detail along this sort of basin or fairway within tNavigator. Okay, so without further ado, let me hand you over to Elliot. I'll stay silent now. So please do share comments, share questions in the box. I'll monitor them, and then we'll try and answer at the end. So thank you, and that's me. And I'll hand you over to Elliot Moore. Elliot, over to you.
Thank you very much, Tom. So, hello everyone, good morning, good afternoon, good evening, wherever you might be in the world. Thank you for joining us today. Tom's already given you a brief introduction to the people online today. So I'm Elliot. I'm a geologist here in the Aberdeen office, again supporting our clients both in the UK and Europe, and helping to obviously drive Geology Designer forward and make it the best possible software it can possibly be, with the help of you, the clients. So, screen on the go here today is the workflow that we're going to follow during our demo that I'm going to give you today. Where we're going to do a little bit of well interpretation. We're going to create Facies using a variety of different tools, different methods that we have available inside Geology Designer. We're going to then move forward and block these logs to our grid. And then we're going to use these logs as long as they capture enough detail from our raw data, and use these to create a variety of different Facies realizations, as Tom said, using a variety of different algorithms that we have available here. So why do we model Facies? Well, ideally we want to capture the known depositional environment of our model by the way of different stochastic and deterministic modeling algorithms. It aids the understanding of the sedimentary environment, where we can use our raw data, our well data that we've been given in question, and helps to capture these geometries of sedimentary subsurface formations in, for example, hydrocarbon-bearing reservoirs. The addition, and what we'll do today, is actually add secondary data or soft data, which will help us to further model and also increase our knowledge of the deposition environment that we have in question here. So we've talked a little bit about block wells. I'm not going to go too much detail today. We're going to do it quite quickly and move on to the rest of the demo. But just a slide here to tell you how we do it inside tNav and how we can QC this. So we have our raw data that we can see in a 3D window here, moving to our block data, and I have turned on the grid line so you can see the individual cells and the Facies that they might correspond to. And then going through into our histogram window where we can start to QC and check the level of detail that's been captured in our blocked wells from our raw log data, and then different ways that we can view this. So we can go into a statistics tab, which is found in our tool palette. We have tool palettes down the right hand side in every visualization window inside Geology Designer, and we can use these to help QC and make sure that we're happy with what we've captured and that we can carry on into our Facies modeling. So again, Tom touched on, we have a variety of different modelling methods, both stochastic and deterministic, found inside Geology Designer that we can utilise to help us build our Facies model. We have different deterministic and stochastic approaches. So we have our kriging, our SIS. I'm sure you're all familiar with these. I'm going to focus around SIS for the first part of the demo today. I'm also going to touch on TGS, or truncated Gaussian simulation, where I apply some geological rules to our Facies. Also, we can interactive model draw, so we can actually draw on our Facies in a 2D or 3D window. And also two of the slightly newer methods that we've implemented inside Geology Designer. We both have object modeling, where we can start to specify things like the azimuth, the sinuosity, the thickness, and the depth of our channels, or our stack channels that we might have in our depositional environment, which I've displayed here on the left-hand side. And then also the use of training images, so we can create a variety of different interactive deterministic training images and use these to help us best model our Facies through multi-point statistics, or MPS here. So back to the workflow slide. What I want to do now is take you into a short demo that we prepared on Facies modeling. It is about 20 minutes long. So if you don't, if you're not sure about anything, or you want to know a little bit more about how we model Facies, hopefully the demo will cover it. If it doesn't, again, please leave any questions that you have in the question box. Again, like I've said, we'll start with some well interpretation. We'll move around, we'll block our wells, create some Facies, move into some variogram analysis. I'll show you how we can create both manual and automated variograms and carry this forward into our Facies modeling. We'll look at some different QC methods, both through cross-section and through 2D. We'll start to apply some secondary data in the form of different trends, whether it be properties or maps. And then at the end, we'll create some Facies models using some different modeling algorithms that we've touched on in previous slides here. So without further ado, I would like to play a demo. So we've started off in well section here. You see what I have toggled on. I've got our 6 wells that we've toggled on nicely here, and I have displayed a gamma log. What I've done is I've actually mirrored the gamma log. So I've created a duplicate of this, and I've created a predefined Facies template that I've color filled. We have 4 Facies in this project, and then moving over into a different well section, I've actually toggled on porosity and permeability also, and I've color filled these accordingly with porosity and permeability. And I've also created a V-shale log, which I've done through calculator statements from my gamma ray, calculating my gamma ray index, and I've color filled the V-shale accordingly to show where we have our shales and where we have our sands. The first place we're going to start and we're going to create a Facies from is our cross plot window. So I've created a polygon earlier around some of our higher poroperm data. Best to note that I've got porosity and permeability displayed here, and I've color filled by our Facies template that we predefined. And you can see now what I've done is filtered out the data that I haven't drawn a polygon around. So I've encaptured this, and we've got our higher porosity permeability that might be our channel bearing or sand bearing reservoir here. What I want to do is create a property from this. The property that I'll create is a Boolean log. So although we've got 4 Facies, we're actually going to see values of 0 and 1. So the lower poroperm values that we have for our data points here will be our shales, and our higher ones according to 1 will be our channels. So if I toggle this on, back in well section, you'll see where we've started to capture initial channels and initial shales and how these correspond to the logs that we've already toggled on. Now, you might all be familiar with if statements. I'm going to calculate Facies log through if statements. So I've applied a series of cutoffs here using if statements where I've used porosity. For example, here you can see I've run an if statement where I've said anything between 12% and 23% would be our levy, our Facies code 2, for example. And I've toggled this on. You can see that it starts to capture that little bit more level of detail where we can see individual packages of sand, individual levies, etc. And going into machine learning, what I want to do actually is pause this video very quickly just to maybe introduce machine learning to you, that maybe those of you aren't familiar with it. I obviously have already toggled on my permeability, my porosity, my gamma ray, and my V-shale that we created previously. And what I want to use is I want to use these logs as our train well logs. I've also specified two particular wells in our project, D3 and D4. These will come up again and again during this demo. These will form hopefully the main channel axes of the channel type environment that we're going to try and capture. And it's going to give us a result well log for all the wells we have in our project and give us a new Facies interpretation. So if I just let the video carry on, you can see that I've specified, toggled on my V-shale, my gamma, my porosity, my permeability, and I run the workflow. And what it will do is it will give us an automated machine learning approach to Facies. So you can see here, it's created another Facies log for us. Again, a slightly different interpretation to the ones that we've previously created through crossplot and if statement, which is good, but we've still managed to capture the main channels again in DW3 here, for example, which is one of the main wells that we use as our train wells there for our machine learning. But we also brought in a raw Facies log to the project originally. So now we have 4 different Facies interpretation that we could take forward into our Facies modeling. But for the purpose of today, what I'm going to do is just use the Facies log that we brought into the project. Another thing that we can utilize is we can actually go into the tool palette on the right hand side and use a tool called edit well logs. What this allows us to do is go into any of the Facies that we've toggled on, whether it be our raw one or the ones that we've created through our if statements or cross plots. We can specify the Facies that we want to maybe paint over. So maybe, for example, here we've got a marker toggled on and we think we should have levy all the way up to that marker. We can paint over the shale that we had and carry the levy on up to the marker. And clicking off this, it will automatically update this, bringing this forward into our Facies. So here I have a top horizon that we've used to build our model, and I've got our Facies templates toggled on in a 2D view. So you can start to see where we might find our channels in our different wells that we have here. And what I've done, as I've said, is I'm only going to take forward the Facies log. I'm then going to block it using a most of averaging technique. And I'm going to toggle my blocked wells on when I find it in our geometry objects. Our geometry objects is found down the left-hand side here. And we can see when I've color filled it using our Facies template as well, how much or the level of detail that's been honored and carried across into our blocked wells. So you can see that our channels and our levies and our shales have been honored quite well here. And again, as I said, I moved into a histogram window so I can QC this further and look at the proportions that we have of our channel, of our shale. Obviously we have an overriding amount of shale in this particular model. We also have our levy and a small lobal Facies as well. And we can go into the statistics panel, which we can select from our tool palette down the right hand side, and we can start to view things like standard deviations, averages that we might want to use later on for some further QC methods, or maybe some more calculator statements to help us QC the model further. We go back into a 3D window. What I've done here is actually toggled on our block wells, and we'll zoom into the DW3 well that I've alluded to so far. And you can actually see the individual grid cells, the Facies that these corresponds to. We can start to see maybe a stacked type channel. And this is before we've applied any sort of secondary data or trends. And we're actually going to go back into our workflow now and run our first level of SIS. I'm going to create very, very manual variograms here. I'm just going to specify a main, a normal, and a vertical range for our shale, our channel, and levy. You'll notice I haven't toggled on lobe right now. We're not going to model the lobe. We're going to come back to this at a later point in the demo. Again, I haven't applied any sort of directional trend, any sort of azimuth to the variograms. I just want to populate the grid with our Facies so far. And whilst this is running, if I take you forward, if I just pause this video again very quickly, this demo very quickly, what I want to show you is when we block our wells to our grid, so here and previously we've blocked our Facies, maybe some porosity, permeability. What we can do is go into our data analysis tab, which is again is selected from the left hand side underneath geometry objects, and we can use the variograms that have been created automatically from our blocked wells, and we can recalculate our directional parameters. We can play around with our ranges, our cells, our nuggets, and specify the variogram type. Or if I let the demo play on, we can actually go into a specific variogram tab inside data analysis and create the variograms very manually, both anisotropic and isotropic variograms. So whether you want to, kind of increase that level of isotropy in your variograms. And you can do this through a variety of things. Obviously, we're going to stick to blocked wells today. We can specify the type of anisotropy we want to use, so spatial, and then we can go in and specify the main, normal, the vertical range, and carry this forward through a couple of button clicks into our Facies modeling and use these variograms going forward. So now our first SIS, or sequential indicator simulation, has run. You can see we've just populated the model so far with our Facies. We don't really see any way of in the way of trends or anything like this. We split screen the model. What I've done is create a cross section through our wells that we're interested in. So again, this is DW3 here. We can see though that our block wells are being honored quite nicely in our first realization of SIS. What I want to go now is back into the workflow and actually apply a second SIS where I'm actually going to apply directional trends. Again, I want to pause very quickly. You'll see how I've bumped up the range for the channel and both the levy to 10,000. The reason I've done this is because the distance between our main two wells are DW3 and DW4 wells, which are going to form the basis of our channel axis system that we're going to try and capture. This is the distance between these two wells, so I want to use this as my main range going forward in my variogram. I've also applied an azimuth to try and capture the directional kind of trend of our channel. I have decreased the ranges for the shale Facies, and I've also kept the levy quite similar to the channel as well, because I want to capture the flanked nature of these levies on either side of the channel. So going forward, you can see now this is run. We've actually started to capture a little bit of a direction from northwest to southeast, and an elongated nature of the channels here. What I've done is I've put the left-hand side, this is our first realization, which is nowhere, no secondary data has been applied, no sort of trends have been applied. And then on the right, we have one where we've applied an azimuth and we've also played around with the variograms a little bit more in the way of secondary data. And what I want to do is look top down on both realizations and actually flick through the K layers so we can see what we have captured so far in the way of any sort of geological data or geological conceptual idea as to what we might be seeing in terms of the depositional environment. And obviously this is only really for our levies and our channels right now, but you can see quite nicely as we go through our K layers, as I simulate through the layers, you can see that we've captured this elongated nature of these channels in some of the layers and also the direction of these two. So moving forward, back to our conceptual image, if I just pause this on this image very quickly, we want to try and capture a little bit more in the way of detail. So we want to add some more secondary data in the way of some more trends, whether this be maps or properties, to capture a little bit more in the way of the geometry of the channel. And maybe play around again with the azimuth, maybe play around with the directional trends that we've already applied as well to best capture the geometry. Now, again, just very briefly, this is quite a busy visualization window. I know I've got a lot of tabs set up here. On the top left, if I just move my mouse over here, we have our well sections, our well templates toggled on with top down with our top horizon that we use to build our model. Top right here is actually a distance from channel property. So I've actually drawn on a polygon, which you'll see me editing in due course. And what we've done is used this to then create some probability properties to look at the probability of when we would have a channel near this polygon, and as we move away from this, how the chance of having a channel decreases as we move to more maybe distal areas of our depositional environment or some deeper marine areas. And again, I've inverted this to create one for our shale as well. So I'll let this play out. And you can see, kind of referring to our conceptual depositional environment that I flashed up previously, we've started to capture the initial direction. And what we want to do is apply some form of trend properties now. So I've set up a split screen, as you can see. I've toggled on a series of these properties. But to create this property, the distance from channel, or to create the properties from the distance from channel property coupled with the polygon, I had to convert and normalize using a calculator statement. I won't show the calculator statement, but to calculate these trend probabilities, obviously we know probability lies within 0 and 1. So we need to capture this and use this as a property going forward to help us best capture these channels, these levies and these shales that I've alluded to so far. And obviously I've inverted the property to capture the shale as well, so vice versa. And these probability properties, if we go into the workflow, can now be applied as trends, and these can help to further our geological interpretation. interpretation. So we go back into the workflow. You can see now how we've started to apply the channel properties and how we've altered the azimuth a little bit more to capture maybe that direction a little bit better from our previous SIS runs, and how we have dropped the shale ranges right down and decreased the levy and channel ranges also to focus solely on trying to correctly capture the Facies proportions in the right areas corresponding to the probability properties that we've calculated. And you can also see this in cross section. So if we run this, what we can actually see when we go back into this window is our next SIS run. You can see if I zoom in, we've actually started to capture, again, a little bit more and more detail now as we're adding more and more secondary detail. Again, I've also toggled on a cross section to show this SIS and cross section view. So I'll zoom in here with my blocked wells. Again, this is DW3, so forming our kind of our main channel axis. You can see that the data is being honored quite nicely so far. Obviously, we've still got a long way to go in terms of adding some more trends and capturing some more detail. What we've also done here is using the SIS property that we've just run, and we've realized in visualization windows, and we can actually use this to create a series of 2D maps. For example, here some proportion maps, thickness maps, or maybe some averaging maps from the probability, channel and shale properties that we created too. But I've actually created a shale fraction, a channel fraction, and a levy fraction map using a proportion method. And going back into the visualization window, we can start to see these. So we can see how the proportions or how the fraction of channel is increased as we kind of are closer to the polygon, to the channel that we're trying to capture from northwest to southeast, and how we can see much more shale as we move away into more distal areas of our depositional environment. So you can see the red values here corresponding, if I just move my mouse, to distal areas here. So back into, I want to actually again, pause the demo very, very quickly. We're going to do very briefly touch on TGS, or truncated Gaussian simulation. I'm sure some of you are familiar with this, where we actually apply a geological rule as well as variograms to our Facies. So you can see here we have shale, levy, and channel that we're going to model and realize again, and also applying our directional trends in the form of azimuths. It would be good to note here that we've got our shale, our levy, and our channel. The order is very important here because each Facies is going to truncate the other. So where we see a shale, it will be truncated by the levy, and then where we see a levy, we should be truncated by the channel. So we shouldn't, in theory, see any channel coming into contact with the shale. So we should see levies bordering the channel. And what we can do is make sure that we're just happy with the azimuth that we've applied. We're going to keep the shale azimuth as 0 again, so we're not going to apply any sort of direction to the shale. We've let this run. We've come back into our split screen here with our 3D TGS and our cross section, and you can see quite nicely we've still captured the elongated nature of these channels, and we can see the levy bordering these channels, and we can see the shale deposited elsewhere. So again, I still think that we can apply more in the way of secondary data to capture or best capture these channels in a little bit more detail. So things like the direction, the sinuosity. So what we're going to do is actually do some object-based simulation now, where we're going to create an object model. And as you can see, we go into or what you would see when you go in and create an object model, we can specify things like the channel width, the channel thickness, the azimuth. Best to note, I'll come back to this very shortly, but we've actually specified a grid property as opposed to a constant value here for our parameter, where I've created a single polygon azimuth property. That is just to best capture the direction of the channels that we're going to model. And again, I've specified the sinuosity length, the amplitude, and I've also used, again, our first realization SIS grid property to set as the target proportions here. So I'll let this run on. So if we're happy with the parameters that we specified, both grid properties and constant values, we can let this run and realize our first object-based simulation of our Facies model. While this is running, what we can do is actually go back into our well section, and we can use the needle tool again from our tool palette, very useful down the right-hand side of any window, and we can actually roughly measure these individual channel sequences. For example, again in DW3 here, which forms the intermediate or the main area of our channel fairway that we're trying to capture here. So I alluded to the single polygon azimuth, so you can see it in 3D and 2D here, where we have our polygon toggled on and the direction that we're trying to capture again, and also the first realization of the object model, where we've tried to capture a little bit more in the way of direction and also sinuosity. So moving forward, you can start to see a little bit clearer here. We also have in cross-section where you can see maybe actually we have an error in DW3 in our main channel axis here. We have a series of stat channels in our channel fairway, and we can see that the data is being honored nicely from our blocked wells into our modeled Facies. So moving on, we want to again allude to the conceptual diagram. We've started to capture that a little bit more in the way of geological detail for our channel. We've started to apply a little bit more in the way of secondary data in the way of trends, both 2D maps and properties. What we want to do is actually start to model these lobes now. So we've left these until now. We want to come back to these and actually start to try and model these. We have lobal areas kind of further down towards the base of the model that we've created. As you can see, if I zoom in here on cross section, we haven't really captured anything yet in the way of our modeled Facies for our lobes. But we want to do this. So how are we going to do this? Well, if you just toggle on for another QC method, our zones property that is output automatically when you create a grid inside Geology Designer, you can see that in zone 2 we haven't really modeled anything. So going forward, we want to try and model this whole depositional environment as we move towards a more distal area where we have these lobes that will appear as the channels become more sparse and spread out that little bit more. So we can run a second object-based simulation where we've applied the channel azimuth as our single polygon azimuth. And we've actually set target proportions this time as 0.45 or 45% for these lobes. And we've set a simulation seed as well. And then going forward, if I pause it very briefly, you can see that I've actually modeled by discrete zones here. So we have 2 zones in our model, and I want to focus, obviously, as I've said, on the second zone because I really want to try and capture these lobes as best as we possibly can. So again, what I've done is gone into the shale, played around with the variogram ranges, applied some more in the way of deterministic approach, some secondary data, and we want to run this and hopefully capture. So I've gone through some of my K layers to come towards the base of our model, and you can see quite nicely top down in 2D there where I've actually managed to capture the lobes quite well. And you can see now if we zoom in again on the same cross section, we've started to capture these lobal features in our depositional environment well towards when we reach towards kind of more deeper depositional areas of our model. And I've also applied a series of arithmetic statements to start to combine these Facies realizations together. Obviously, we want to go back in and model as best as possible our channels, our levees, our shales, and our lobes. So you can see here we're starting to honor all the data. We've applied a series of different secondary data steps in the form of, as I said, we've created a number of 2D maps, we've created a number of 2D properties, and we've applied these accordingly. We've played around with our directional trends, we've played around with our azimuths, and you can see here in 3D and in 2D side by side, we've actually started to, through object modeling and through SAS, capture quite nicely our model. Now moving forward, there's other modeling algorithms that we can actually use in Geology Designer that I've previously specified on, where we might not necessarily be using variograms to apply secondary data in the form of trends and 2D maps, etc. So what we can actually do is move forward and use some multi-point statistics, or MPS, which I previously touched on in some of the slides that I showed before the demo. So we've created an MPS workflow also. Before we can run any sort of MPS, we have to create a regions property. So we have to split the model into specific regions. So I'm going to split it into 3 regions, 1, 2, and 3, to best capture the green area, which is our kind of feeder channel, the purple area encompassing DW3 and DW4, our main channel or intermediate area, and then the yellow area being more distal, the red areas you see being undefined. And you can see I want to create a series of training images in 2D and use these as secondary data to help us best model our depositional environment like so. What I'm actually going to show you is how to create one very quickly in this demo. So if I take the brush horizon from the tool palette on the right hand side again in 2D, I've got my 2D windows set up quite nicely here. I can specify the Facies code, so we know the Facies code of 1 corresponds to a channel, and I can very easily draw on a sinuous channel on our 2D training image. I can go back in, and maybe this wants to be flanked by a levee, so I want to capture the levee as well. I can draw on either side of the channel the levee. Now, I must stress this is not the training image or one of the training images we're going to carry forward into our modeling. I just wanted to show you the ease of use of the tool and how we can utilize this tool and create a number of different training images. I'm only creating 3 for this particular depositional environment that we're trying to model, but it's important to stress that we can create hundreds of these training images and carry these forward into our MPS modeling. Again, we go back into an object-based simulation for first, and we want to create a resulting property. We've applied a certain constant values to our object model to capture our feeder channel here. So you see again the northwest to southeast directional trend that we've applied. And we want to capture this, obviously not through variograms this time, so we have to draw on manually and run an object-based simulation to capture this as best as possible. And we've got our 3 training images that we're going to carry forward. So now we have run our MPS. I'm going to pause again very briefly. It's important to note that the Facies codes and the training values and the Facies values need to match up here. So we created a Facies template previously where we specified our shales as 0, our channels as 1, our levies as 2, and our lobes as 3. Now we need to make sure that these all match for our MPS to be carried out accordingly. And we need to create a series of MPS realizations using each individual training map. So you see here I've specified my intermediate. So if you can remember the kind of the body of or the region body that we want to use to calculate or specify our main channel area. So I'll let it run out. We're going to forget about the lobe for now. Again, we're just going to focus on the shale, the channel, and the levy. But for the outer area, when we reach more distal, obviously we need to model the lobe accordingly. So we only model the lobe when we need it. And we can hit run. And then we can move into arithmetic statements. We need to combine these as best we possibly can. So we need to select a number of if statements or create a number of if statements to amalgamate and join these MPS realizations together and then run this so that we can best see where our feeder channel lies. So again, you have, if I pause very quickly, our feeder channel here from the northwest traveling to the southeast. We have our main body of channels in here forming the channel axis where we can see DW4 and DW3. And then coming down into more deeper marine distal areas where we can start to model the lobe that's a little bit clearer. But we have to join our MPS realizations all together. So through a series of if statements, we can get rid of our other Facies and show where we have our main body, where our channels are flanked by our levies, and in our final realization where we can see, again, the lobal areas in more distal areas. And if I flick through the K layers again, you can see quite nicely that we've started to capture very well through the addition of secondary data through our training images, our model quite nicely. I've also created a user cut here to get rid of the shales, so you can just see the 3 Facies that we're really keen on capturing in this depositional environment. So you can see our main body of our channel, and then moving forward into more distal, kind of deeper marine areas where we started to capture these lobes where our channels start to disperse as we reach maybe a more deeper marine environment. So what I want to do now is pass you back over to Joanne. I know it was a very brief demo. I hope you enjoyed it. So pass you over to Joanne.
Thank you, Elliot, for the presentation. We are running out of time a little bit, so I'll just give the guys a couple of minutes to look through some of the questions. And our next webinar will be on Thursday at 3 o'clock UTC, which is 4 if you're in the UK. And that's modelling depositional sequences with Joe and Jessica. So I can see there are quite a lot of questions coming through. Do you have a couple that you'd like to answer, Tom and Elliot? Just maybe 2 or 3?
Yeah. Can you hear me okay, Joanne?
Yeah, it's fine.
Perfect. Yeah, there are quite a few questions coming in. I think I'll answer probably 2 or 3 of them because I think of time. But yeah, we'll definitely follow up on all the questions after the webinar. But just a few right now. I see there's one come through about at the end of the Facies modeling process, is it possible to calculate vertical communication, i.e. fraction or contacts between sound bodies? So in tNavigator, we do have various means of doing this actually. So it could be through various attributed maps, through properties and 2D maps to calculate things like thickness or fraction, but also for actual sand bodies, we have things like attribute connect, I think it's called connect bodies or connected volumes attributes that we can calculate within tNav to calculate certain Facies or a discretized body that we want to, and then we can understand the percentage there if that's possible. So the other one we have here is related to the object modeling. Are attraction or rejection of objects in order to simulate levels of amalgamation and more complexity. So a little bit of a mouthful, but in simple terms, so everything that Elliot talked about today, and you will see that he actually used our automated sort of workflow wizard, let's call it. You can do things through manual processes, but this just means actually that when you want to take things to things like to uncertainty, you can start to initialize any of the parameters as variables. So where I'm going with that is if you were to take in object modeling, you can start to play around with the dimensions, sinuosities, wavelengths, bits, thicknesses, anything you kind of put a number to or property to. You can start to initialize these as variables and start to play with your geometries that way through uncertainty analysis. Okay. And then one more question I think was related to. Let me just see what we did through here. Is there possibility to use Facies weight or block logs or scaling to retain thin shales? So not directly in the blocked logs. I know we're talking about. I know the process you mean, but we do have other means. We didn't talk about things like vertical proportion curves, where you can modify proportion, obviously the proportion of discrete value or Facies or log type within a layer. And also we have something called like declusterization, I believe, that allows you to manipulate some of the weighted distribution values per layer or per zone, etc. So I think that's all we have time for, to be honest. But I will definitely follow up with all the rest of the questions. There were many more questions that came through. But I will definitely follow up with the rest of the questions with some information about forward development for Facies modeling, because I know there's a question on that as well. So yeah, thank you, Joanne.
Thank you very much, Tom. Yeah, thank you very much, Tom and Elliot, for your presentations today. And as Tom said, we'll follow up with all your questions, and we will see everyone on Thursday. Thank you and enjoy the rest of your day.